Today in the workshop, we'll be working with an analog feedback servo motor. We'll see how this motor differs from a regular servo motor and how to use it to improve servo performance. We'll even use the motor as an input device to record and play back servo movements. We're getting some feedback today, so welcome to the workshop. Hello and welcome to the workshop, and we are going to be working with a servo motor today. A bit of a different servo motor than the types of servos we've worked before. This is an analog feedback servo motor. Now, a regular servo motor, which we've used in many of our projects and which I even did a separate video about, is a DC motor that is geared down so that it has a lot of torque and low speed on the output, and it's also restricted to traveling between two positions, usually 0 and 180 degrees or 0 and 270 degrees, and any position, of course, in between. The thing about a servo motor is, in addition to a power and a ground lead, it also has a control lead. And on an analog servo motor like the type that we've used before, the control lead accepts a pulse width modulation signal. That signal tells an internal feedback mechanism in the servo where to position the motor. And that feedback mechanism consists of a control circuit and a potentiometer. When the motor shaft moves, the potentiometer moves, and it feeds back that information to its control circuit, so the circuit knows when the servo has gotten to the desired position. Well, in an analog feedback servo motor, the output of that feedback mechanism is also brought out so that we can read it with our microcontrollers, such as an Arduino, and this is an analog signal that changes voltage as the servo changes position. And this can have a number of advantages. For one thing, with a regular servo motor, we really don't know where the shaft actually is at any given moment when it is moving. We know where we start, we know where we finish, but in between we have no idea where it is. This comes into play when we're designing Arduino sketches to drive servo motors. We need to put a small time delay in every time we move the servo motor because we need to account for the time it takes for the servo to move from one position to another. And in most cases, we apply a fairly large time delay to allow the servo to move all the way in its travel, such as from 0 to 180 degrees. But that's too long a delay to use if we're only moving 3 or 4 degrees, and in some cases that can cause our mechanical devices to move erratically. Another thing you can do with an analog feedback servo that you can't with a regular servo is you can use it as an input device. If something external moves the servo shaft, you can feed that information back to your Arduino and get an idea of where the shaft actually is right now. And you can use that to a lot of advantages. In fact, we're going to do a demonstration where we move the servo shaft manually and then play it back with the Arduino. So there are a number of advantages to using an analog feedback servo. Now, you can make your own analog feedback servo by modifying a regular servo motor. You can open it up, find the potentiometer, take the center wiper connection to that, and feed it out of your servo motor. But you can also buy commercial analog feedback servos, and they're not much more expensive than regular servo motors, and that's the type of servo that I'm going to be using today. So let's get started by learning a bit about analog feedback servos, and then we'll move on to some experiments with them. So let's examine the analog feedback servo motor. An analog feedback servo motor is a servo motor that has an additional output from its internal potentiometer. This allows a controlling device, such as a microcontroller, to dynamically read the motor shaft position. The output is an analog voltage which is proportional to the position of the motor shaft. This type of servo motor can also be used as a regular servo motor. This diagram illustrates the operation of a regular servo motor. A control input is fed in from a microcontroller, and this feeds into a servo control circuit inside the servo motor. The servo control drives the motor in the appropriate direction, and the motor shaft is coupled to a potentiometer. The output of this potentiometer is fed back into the servo control. This is called a closed-loop system. In the analog feedback servo motor, the feedback signal from the potentiometer is also fed out of the motor and back into the controlling microcontroller, giving a dynamic indication of the current position of the motor. The analog feedback servo motor we'll be using today is called an S1213. It has the following connections. The white wire is the feedback output. The orange wire is the control input. The red wire is the power supply. The motor accepts a power supply of 5 to 6 volts DC. And the brown wire is the ground. The motor has the following specifications. It has a torque of 4.5 kilograms centimeters, which is the same as 62.5 ounce inches. It has a speed of 0.23 seconds to rotate 60 degrees. And the motor weighs 40 grams, which is 1.41 ounces. Let's take a closer look at this motor now. So here's the S1213 analog servo motor. As you can see, it looks like a pretty standard servo, and it comes complete with a small assortment of horns and a set screw, just like most servo motors do. Of course, the main thing about this servo motor that's different is that in addition to the standard servo connection over here, we also have this white wire, and this white wire is, of course, the analog feedback wire. This is the one, the output from the internal potentiometer in the servo, that we can use to externally measure the servo position. So, as I said, it's pretty well a standard looking servo motor with the exception of the extra lead, and it's just as easy to use as any other servo motor. So now that we know how an analog feedback servo motor works and we've taken a look at one, it's time to put it into use. Now the first thing we're going to do is run a small calibration sketch. And what this sketch is going to do is it's going to move the servo into various different positions, and it's going to read the output from the servo's feedback mechanism. And of course we're going to read that output, which is a voltage, using the analog to digital converters in our Arduino. Now this will allow us to calibrate our servo so that we can use it in future sketches. So let's go and take a look at that sketch right now. Here's what we'll need to hook up our first experiment. We'll need an Arduino Uno, an S1213 analog feedback servo motor or the equivalent, and a 5 to 6 volt DC power supply for the servo motor. Now you can use the 5 volt supply from the Arduino if you wish, but I would not recommend it as the motor may induce excessive noise into the Arduino. If you do decide to do that, I'd also recommend using a decoupling capacitor to limit some of that noise. We'll start by connecting the ground from our external power supply to the ground on the Arduino. Next, we'll connect the motor ground, which is the brown wire, to that same ground connection. We'll connect the positive from the motor power supply to the motor's positive input. This is the red wire on the motor. We'll connect the motor's feedback output to the analog A0 input on the Arduino. This is the white wire from the motor. And finally, the motor control input is connected to pin 9 on the Arduino. This is the orange wire on the motor. And this completes our hookup. Here's the sketch that we're going to be using as a calibration demonstration for our analog feedback servo motor. Now it's a pretty simple sketch. It starts off by including the servo library, which is a built-in library in your Arduino IDE. Next we define a couple of pins. So we define the servo pin being the one that the control pin for the servo motor is hooked to, and the feedback pin, which is the analog A0 input that the feedback output is connected to. I've also defined another integer called feedback value, and that's just going to read the value from that A0 pin. We create a servo object, we're calling it myServo, and we go into the setup, which is where all the action occurs in this particular script. We'll start off our serial monitor so we can see what's happening, and then we'll attach our servo to the servo pin. Then we home the servo motor, so we just do a write to position 0, and that sends the servo all the way to one end on what we would call the 0-degree position. And everything now goes into a for loop over here. And we're going to step everything by 5 degrees. So we define an integer called the servo pause that indicates the servo position in degrees. And we start off as 0, and we'll go all the way up until it is 180. And then we're going to increment everything by 5 degrees. And that's what this little bit of the for does. Now, if you want to change it from 5 degrees, you can just change this number over here. We'll start off by positioning the servo motor to the value of servo pause. We'll allow it some time to get there and also some time to display on the serial monitor. Now, I've delayed by a full second, which is far too much. You could actually set this down to about 50 milliseconds and it would work, but everything will go by pretty quickly on the serial monitor, and I wanted you to be able to watch everything happen. And then we'll read that value, so we'll take an analog read of the feedback pin and assign that to the feedback value, and we'll simply write that out to the serial monitor. So we'll write out the servo position, this is a tab character, and then we'll write the feedback value. And the loop continues until we've got to the 180 position. Then after that, we'll home the motor again by writing it to 0. We'll write to the serial monitor that we're finished, and we're essentially done. There's nothing in the loop of this sketch. So let's load this up to our Arduino and watch it work with our analog feedback servo motor. Here's my calibration test setup. It's actually pretty simple. You can see, of course, the analog feedback servo motor here. In the background, you'll see the Arduino, and coming off the side, you can see part of the connections that I'm using from my 5-volt bench power supply to give the motor some power. And so what I'm going to do is I've got my serial monitor up. I'm going to reset this and just let it run. And as you can see, it's stepping in 5-degree increments, and it is giving a value, and that value is the calibration value. And you can use that in other sketches that you build with the analog feedback servo in order to calibrate the motor more accurately. And we're coming up near the end now, and it returns. And so that's it, our very simple calibration sketch for the analog feedback servo motor. Now, at the beginning of the video, I had mentioned that you could also use an analog feedback servo as an input device, and that's exactly what we're going to do in our next demonstration. Now, the sketch and the wiring for the next demonstration are not something that I came up with myself. This is something that Adafruit has produced and they've released into the public domain, so I'm just going to be repeating it over here. But what it is going to do, it is going to allow us to move the shaft manually by hand, store those values into EEPROM, and then play them back. And there's going to be a couple of push buttons we can use as basically a record and a play button. So let's go and take a look at that right now. For our servo as an input demonstration, we are going to start off with the same wiring as we did in our last experiment. We're going to add some additional components. We'll add an LED, a 220 ohm dropping resistor for that LED, and 2 push button switches. One will be our record button and the other will be our playback button. We'll begin by connecting the LED anode through the 220 ohm resistor to pin 13 of the Arduino. We'll connect pin 12 of the Arduino to one side of the record push button. Pin 7 of the Arduino will be connected to one side of the play push button. And finally, we will connect the anode of the LED and the other side of both push buttons to the Arduino ground. Now let's take a look at the sketch we'll be using. Now this is a sketch that Adafruit has provided for recording and playing back the movements of an analog feedback servo motor, and it's an interesting sketch. It starts off by including two libraries, the servo library and the EEPROM library, and both of these libraries are built into your Arduino IDE, so you won't need to install anything extra. We also define a couple of calibration points over here, the minimum and the maximum ones. Now these values came with the sketch, but if you ran the last sketch, you could actually improve upon them and use the values that you derived by running the last sketch for minimum and maximum. It also incurs a sample delay that we set up as a sample delay constant. Interestingly enough, they've set it at 25 milliseconds here, even though a note over here says 50 milliseconds seems good. Now I've kept it as it is, and it seems to work fine. Then we define all of the different pins that we are connecting to. So the record and play buttons, the servo pin, which is the control pin for the servo motor, the feedback pin, which is the pin coming from the feedback, which goes to analog A0, and the LED pin on pin 13. And then we set up an object for the servo called myServo. Now in the setup, we start off by initiating the serial monitor, and these two lines here are rather interesting. Now if you recall the schematic diagram for this, we have the two push buttons connected to their inputs with the other side connected to ground, but there are no pull-up resistors on them. This is how we get around it. First you do a pin mode to the button and set up as an input, and then you do a digital write to it and write high. Now it may seem a little odd to write to an input, but what this effectively does is it holds it high, and so when the button is pressed it'll bring it low, and this way we don't need any pull-up resistors. It's rather ingenious actually. You do the same for the play button, and we set the LED pin up as an output, and then we print out to the to the serial monitor, and we begin our program. Now the program happens inside the loop. We'll look at the loop first and then at the functions that we call from the loop. Now all of this over here is basically done to debounce the push button. So this is the one for the record, and once it's been debounced, we call a function called record servo. If it's the play button, we do the same thing and call a function called play servo. Let's go take a look at those functions. We'll move all the way down to the record servo one first. Now in record servo, we'll print to the serial monitor, and we'll send the LED pin high to turn the LED on. And then we'll go and we'll read the analog input. We'll read that analog pin, the feedback pin from the motor, and assign it to the variable A. And then we'll print that out to the serial monitor, and over here we recheck our calibration. If we happen to get a minimum value that's lower than the minimum or a maximum that's higher than the maximum, we'll reset our calibration values. Otherwise, what we do is we map everything out to a value of 0 to 254. So we're doing a range of 0 to 254. Note that it's not 255, but it's 254. 255 is going to be used as a flag character, as you'll see in a moment. Then we print this out to the serial monitor, and we write it to the EEPROM. And then we increment the EEPROM address, and we check to see if the address has reached 512, because that's the number of address spaces we have in the EEPROM in an Arduino Uno. If it is, we break out of this. Otherwise, we delay by the sample delay and keep going and keep going. Now, once we've broken out of it, we check to see if the address is not 512. If it is, we don't worry because we filled up the EEPROM. But if it isn't, we write the value of 255, and that's sort of a flag to say, hey, we've reached the end. This would occur if you stop recording before the EEPROM is full. Then we'll send the LED pin low to turn off the LED, print done, and delay things a little bit. Now let's go and take a look at what happens when we play back. When we play back, again, we'll print out to the serial monitor, and we will read the EEPROM, and we'll print out its value, and we'll take a look. If it is equal to 255, then we'll break, because that's the character that says we've finished everything. Otherwise, we'll map everything out to a range of 0 to 180, which is what the servo motor wants to see, and then we'll print that out to the serial monitor. We'll write that to the servo to move it into that position, and we'll delay by our sample delay, 25 milliseconds in our case, increment the address, and keep going until we get get to 512, which is the end of the EEPROM, and we can break. Of course, if we stopped sooner, we would have broken over here where it read 255. Then we print done, we detach from the servo motor, and we delay. So basically, the function of this is to record and then to play back the servo motor motion. So now that you've seen the sketch, let's take a look at it in action. So here's our recording servo demonstration. Once again, I've got my servo motor and the external power supply back here that's feeding the servo motor. I've also got my LED, the dropping resistor, and the black button over here is my play button, and the red one is the record button. I've also got my serial monitor running. So I'm going to grasp the motor because it's good to hold on to this when you're doing this. I'm going to hit the record button, and the red light comes on, and as you can see on the serial monitor, it is recording positions. And we'll continue to do this while it is still recording. Hopefully you can see that and then the light's gone off. And so now we finished recording our sequence. Let's hit the playback button and see what happens. And there we go. It's playing back the sequence that we recorded. And of course I can play it back a number of times, so I can hit the button again. And as you can see, it's going through the sequence again. And so this would be great for some sort of an animated display that you wanted to record a complex motion for. And I think it works very well. Alright, so that brings us to the end of this video on analog feedback servo motors. I hope that you enjoyed it, and I also hope that it's inspired you to start using a device like this in some of your own projects. Now, if you need a bit more information, or if you want to get the sketches that I've been using today, head over to the dronebotworkshop.com website, where you will find an article that accompanies this video, and there's a link to that right below the video over here. Now, while you're on the website, if you haven't signed up for the newsletter yet, please do. It's my way of keeping in touch with you and letting you know what's going on in the workshop. Now, if you want to discuss anything that we've talked about today, the very best place to do that is on the DroneBot Workshop forum. You'll also find a link to that below the video. And on the forum, you can discuss this or any of the other videos that I've done, or basically anything about Arduinos, Raspberry Pis, or robotics, or any form of electronics. We've got a lot of really great people on the forum and a lot of very lively discussions, and I urge you to become part of that. So until we meet next time, please take care of yourselves, and I hope to see you again very soon here in the workshop. Goodbye for now.